హలో హలో చెప్పండి. అవునండి. ఏం సబ్జెక్టు? ఎంకామ్. నువ్వు కెమిస్ట్రీ డిపార్ట్మెంట్ కాల్ చేసి ఎంకామ్ గురించి నాకు తెలుస్తుంది. నోటిఫికేషన్ మెయిల్ వస్తుంది, చూసుకోండి. అంబేద్కర్ ఓపెన్ యూనివర్సిటీ వెబ్సైట్ చూసి నెంబర్ చూస్తే అక్కడ అన్ని డీటెయిల్స్ ఉంటాయి. ఎవరికి కాల్ చేయాలి అక్కడ చూస్తే తెలుసు. అంతేగాని ఆన్లైన్లో దొరికిన నెంబర్ అన్నిటికీ చేస్తే ఎట్లమ్మా? చెప్పు అశోక్. అట్ట. అవును అవును, నేను చెప్తే నన్ను ఊరుకోడు, నన్ను తిట్టి పెడతాడు. నువ్వే చెప్పినవా అని అన్నావు అనుకో, నాకు తెలిసింది అనుకో ఆయనకి.
లేదు సార్, మనం వేరే కూడా అన్నారు ఈరోజు
నాకు తెలిసి రాకపోవచ్చు. వస్తారా? Good morning, students. Today we are going to discuss about the metal carbonates and metal nitrosates. This is the first unit in the sixth semester course material. Now I'm going to start metal carbonates and the metal nitrosates. Now, what are the metal carbonyls and metal nitrosates? Metal carbonyls metal nitrosates are metal carbonyls. These are the metal ion which is form a complex with carbonyl or carbon monoxide or NO are known as metal carbonyl complexes or metal nitrosyl complexes. Metal carbonyls and metal nitro and their related compounds are most commonly found are found by the several metal ions in the periodic table. The formation of metal and carbonyl and nitrosyl complex is general characteristic feature of d block elements. Now coming to molecular orbital energy level diagram for the carbonyl compounds. First, we can take the molecule of carbon monoxide. This is an example of the diatomic molecule, which is a sigma donor. It is example for the sigma donor, that means it donates a sigma pair of electrons, and an excellent pi acceptor. If it is there any metal ion or any central atom which is ready to donate the pi electron density to the carbonyl, it can readily accept. It forms complexes. It forms complexes with metals in low oxidation states, and most often it forms in an oxidation state of 0. That is the carbonyl and nitrosyl, which is in the metal complexes found with the 0 oxidation state. But sometimes also it is in a low positive and low negative oxidation states. It shows low positive and low negative oxidation states in the complexes. The complexes of carbonyl with metal are called as metal carbonyls or simply carbonyls. The valence bond structure of carbon can be shown: two non-bonding electron pairs and one on carbon and other one is on oxygen. The carbon monoxide is a good potential ligand character in metal carbonyl complexes. If we consider the molecular orbital energy level diagram for the carbonyl, we can take this is the carbon. In this outer electronic, if we consider the electronic configuration of the carbon 1s2, 2s2, 2p2, and oxygen 1s2, 2s2, 2p4. Now, one side you can take the carbon, on one side you can take the oxygen. You can take the valence orbitals of the atomic orbitals, which combined are undergoing the linear combination of atomic orbitals combined to molecular orbitals. These 1s orbitals both will combine to give this molecular orbitals. There is a sigma and sigma, one sigma and one sigma star. This is the bonding molecular orbital, and this is the anti-bonding molecular orbital, sigma star. Whenever we consider the two s orbitals of the carbon and oxygen, which are undergoing LCAO, okay, linear combination of atomic orbitals produces 2 sigma and 2 sigma star molecular orbitals. This 2 sigma orbital is the bonding molecular orbital, and 2 sigma star is the anti-bonding molecular orbitals. When you coming to carbon, when you come into the carbon, it is having 2p atomic orbitals and oxygen 2p atomic orbitals. When you compare the energy, this oxygen 2p orbitals are slightly lower energy than the carbon 2p orbitals, which will combine to give three molecular orbitals and three antibody molecular orbitals. In that, in that, one of them 1 5 and 3 sigma, and 1 5 star and 3 sigma star are the six orbitals are molecular orbitals are generated. These are the, if you consider that this 1 5 orbital is pi x and pi y orbital and two sigma electrons, when you assign the filling of these electrons, two sigma orbitals, two sigma electrons here, sorry, this phi x and phi y is filled with the, how many electrons are there in the 2p? 2 plus 4, 6 electrons are there. Now these 6 electrons are filled in, first two electrons filled in phi x and phi y, again 2 electrons filled in phi x and phi y. These are filled with, that is phi 2x, phi 2y, 2 electrons, 4 electrons are there. The remaining 2 electrons filled in 3 sigma. Now the anti-bonding molecular orbitals are vacant. Now, wherever the electrons present in the highest energy molecular orbital, 3 sigma, class ఏం చేస్తాం మేడం స్టూడెంట్స్ 10 minus 4 by 2. That is 6 minus 6 by 2 equal to 3. Therefore, 3 is the bond order. Bond length is 1.14 angstrom between the carbon and the oxygen. It is bonded with uh, C triple bond O. Now, if you discuss detailedly, its bond order is 3, that is 10 minus 4. That is, the length is 1.14 angstrom, existing with a triple bond. That means the bond order is 3 and the length is 1.14, existing with the triple bond. The HOMO of the carbonyl molecule is almost non-bonding, sigma bonding, non-bonding and sigma orbital, largely located in carbon. The LUMO is anti-bonding, 5 molecular orbital. The HOMO is highest occupied molecular orbital, that is 3 sigma, and LUMO is lowest unoccupied molecular orbital, that is 1 5. Carbon monoxide is a heteronuclear diatomic molecule. The electronic configuration is Z is equal to 6. That is 1s2, 2s2, 2p2, and oxygen Z is equal to 8. That is 1s2, 2s2, np4. So the carbonyl molecule contains 14 electrons. The simplest carbon atom and oxygen atom combined with to form a molecule with the triple bonds. That is, in which one is a sigma bond and two are the pi bonds. The carbonyl molecule orbital energy diagram arranged 14 electrons, that is in 10 in the bonding molecular orbitals and 4 in the anti-bonding molecular orbitals. The carbon monoxide molecule is the HOMO is 3 sigma, which is largely non-bonding lone pair of the carbon atoms. The LUMO is the doubly degenerate pair of anti-bonding orbitals. There is one 5 star orbital with mainly two p orbitals character. Next, the combination of the frontier orbitals, a full sigma orbital largely localized on carbon atom, and a pair of empty 5 star orbital due to this. In metal carbonyl, the HOMO lone pair of carbon oxide is right. Right. Okay. Now coming to just a minute. Now where L is the ligand is equal to carbonyl group. The metal is combining with the ligand, it is carbonyl group. Now the ligand is donating to the electron pair to the metal, that is sigma bond. Sigma bond between the here the LUMO is participating. The LUMO is it is the donor. A ligand is the donor, and there is a sigma bond is formed between the ligand and the metal. Now the metal is donating to the ligand electron pair to the ligand. That is pi bond. That is the here the ligand is the acceptor. When you discussed the acceptance of this pair of electrons or donation of this pair of electrons can be represented in the form of orbitals. Yeah, look at it. Here the carbonyl compound, the carbonyl group is donating its pair of electron to the metal. Now it is formation of involving a sigma bond between the metal and the carbonyl group, a carbonyl ligand. Now here the metal orbitals, d orbitals containing the electrons is donated to the anti-bonding molecular orbitals of carbonyl. It is the LUMO. It is accepted by the LUMO, then it forms the 5 bonds. There is a 2 5 bond formation which takes place that leads to the formation of sorry, carbon metal 5 bonds, right? The metal bonding modes in the metal carbonyls, bonding modes of metal carbonyls. There are 4 types of bonding modes shown by the carbonyl compound, carbonyl groups with the metal ions. Or during the metallation, it shows the four kinds of bonding modes. One is the terminal carbonyl bonding and bridged carbonyls, that means semi-bridged carbonyls and triply bridged carbonyl bonding. That means the carbonyl is existing in terminal. Here the carbonyl is attached with the metal with the bridged bond, and here the carbonyl is bonding with the metal ion with the semi-bridged. And in the fourth case, the carbonyl is bridged bonding with the metal with the triply bridged. That means triple bonds, triply bridged structure is generated. When you coming to the terminal, first one terminal carbonyl compounds. Here, this is the example. Ferrous is attached with 5 carbonyl ligands, in which all are bonding with the single bond. Most of the are sigma bond with the iron and carbonyl. Here, the IR spectra of this carbonyl shows at 2143 peak centimeter per speed. That indicates that the greater than the terminal ligands always shows that this range of IR band in the IR spectrum. Next, we coming to the bridged carbonyls, metal carbonyl symmetric carbonyl. Here the M2C2 metal ions are there. Suppose the two metal ions are bound with the same carbonyl group, that is called bridged carbonyl group. Now when you coming to this ferrous CO taken 9. In this complex, ferrous is attached with 3 carbonyls with the bridging bond and 3 carbonyls with the single. That are terminal carbonyls are there. In the semi-bridging, here the M2CO, this kind also osmium, OS4 CO taken 14. In this you can see this. This is the semi-bridged. This kind of carbonyl structure is called semi-bridged structure. In this, if you see that it shows the 1900 centimeters to 1800 centimeter units. Then triply bridging ligation are triply bridging carbonyls. Just terminate. Okay. This is the triply bridged ligation, the triple bridging carbonyl, metal carbonyl. In this, you see that same one carbonyl group is attached with the 3 metal ions. This is called triply bridged ligation. Example for the triply bridged ligation is rhodium taken 6 and CO taken 16. This triply bridged IR spectrum is in between the 1700 centimeters to 1600 centimeter inwards. The peaks will be appear in the air spectrum is 1700 to 1600 centimeter inwards. Now, metal carbonyl complexes. How these metal carbonyl complexes are generated? Many of the transition metals form compounds in which carbonyl act as ligand. Carbonyl is a very, or carbon monoxide is a very strong Lewis base, and it to form storing bonds or forms strong bonds to the metals in these complexes. The metals are low oxidation state, most often in an oxidation state 0, but sometimes also in a low positive or low negative oxidation states. Many of these metal carbonyl compounds obeys 18 electron rule. The transition metal and they combined with the group of ligands will form the complex is called metal carbonyl complexes. These metal carbonyl complexes are divided into different types, that is mononuclear, dinuclear, trinuclear, tetranuclear, and polynuclear metal carbonyl compounds. In the case of mononuclear metal carbonyls, CO stretching frequencies are different in metal carbonyl compounds based on its symmetry. For example, you consider the nickel carbonyl compound where the carbonyl stretching frequency is 2125 centimeters. That is TD, tetrahedral symmetry, and Fe ferrous carbonyl, FeCO 5 taken 5. The CO stretching frequency is shown at 2002 centimeter inverse. It has D3H symmetry, but chromium carbonyl is at 2000 centimeter inverse. It has octahedral symmetry. In this, all metal carbonyl bonds are terminal only. The range of carbonyl stretching frequency 2125 to 1850 centimeter inverse. You see, this is the chromium carbonyl. This is the ferrous pentacarbonyl ligand. This is the dinuclear. When you come to the dinuclear, this is a mononuclear first two. They are paired at 2002 centimeter inverse. When you coming to the dinuclear and trinuclear, this is the Mn2CO taken 10, Fe3CO taken 12. This is the trinuclear. In the dinuclear, manganese carbonates Mn2CO taken 10. And trinuclear, if you take one ferrous and three ferrous metal ions and 12 carbonyls. If you take the carbonyl cobalt complexes, in which three carbonyl, three cobalt, in the dinuclear carbonyls, if you consider the cobalt complex, that is 6 plus 8. Cobalt taken twice and carbonyl taken 8. This is the dinuclear. We have several examples for this. These are the primary three examples for the dinuclear and trinuclear. Next, tetranuclear metal carbonyls. In the tetranuclear metal carbonyls, cobalt 4 CO taken 12. This is the bridging. In the case of iridium complex, iridium carbonyl terminal, all the carbonyls are terminals. Now, when you're coming to the 18 electron rule, this is also called Sidgwick rule and EAN rule. In this, the sum of the electrons on the metals plus the electron donated from the ligand was called the effective atomic number. EAN is already learned in the D block elements, and when it was equal to any noble gas electronic configuration, the rule was said to be obeyed. Suppose if we consider any metal carbonyl, the number of electrons are associated the bonding around the metal with the ligand, the total number of electrons are reached to the nearest noble gas electronic configuration is known as effective atomic number. Whenever it is having that effective atomic number, that obeys that rule, 18 electron rule. Now, when a metal achieve an outer shell configuration is ns2, n-1 d10 and np6, there will be 18 electrons in the valence orbitals, and a closed stable configuration was called as 18 electron rule. Electrons counting in complexes, suppose we consider the chromium carbonyl complex, where the chromium is atomic number is 24. Its valence electronic configuration is 3d5 4s1, which is having 6 electron and 3 valence valence electronic configuration. And where the six carbonyls are involved in the complex, therefore 2 into 6 carbonyls, that is the 12 electrons are there. 12 plus 12 electrons from the carbonyls and 6 electrons from the chromium, total 18 electrons. Therefore, the chromium carbonyl complex is obeys the 18 electrons, which is having the formula CrCO taken 6 is having 18 electrons. Therefore, the complex is obeys 18 electron rule. When you consider the Fe3CO taken 12 ferrous carbonyl complex, in which ferrous is 26, Fe is 26 molecular weight, atomic number, and its valence electronic configuration is 3d6 to 2s2. The total electrons, outer shell electrons are 88 electrons. Now it is attached with the total 12 carbonyls, 12 into or 2, total 24 electrons. Here the three ferrous metal ions are there, therefore 3 into 8, 3 into 8 24, 24 plus 24, that is 48. Now the three metal ions bond with three electrons, three bonds with two electrons. These three metal ions are also established with the metal bond, ferrous bond. Therefore 3 into 2, total 6, 48 plus 6, total 54. 18 into 3, 54. Therefore, each metal ion is carries the 18 electrons. Therefore, the ferrous Fe3CO taken 12 metal complex follows the 18 electron rule. Next, preparation and properties of nickel carbonyl complex. Nickel carbonyl complex preparation. The nickel is directly react with carbon monoxide at 60 to 100 degrees centigrade to form the nickel carbonyl complex. That is, nickel is directly treating with the carbonyl at 60 to 100 degrees centigrade. That directly generates the nickel carbonyl complex. Or instead of nickel metal ion, you can take the nickel iodide with the equivalent amount of carbon monoxide at copper, in presence of copper lining, that leads to the formation of nickel carbonyl along with the copper iodide. Nickel sulfide is also reacting with the carbon monoxide, that leads to the formation of nickel carbonyl with a free sulfur. Next, properties. When you come into the properties, it is a colorless ligand. Carbonyl is the colorless ligand. Melting and the metal complex is carbonyl, when it is solid, then therefore it is carbon monoxide is solidify at below minus degree centigrade, therefore it melts, its solid melts at minus 25 degrees centigrade, boils at 43 degrees centigrade, minus 43 degrees centigrade. It is insoluble in water but soluble in organic solvents. It reacts with sulfuric acid to form nickel sulfate. Nickel sulfate. That is, nickel carbonyl is treating with H2SO4. It leads to the formation of nickel sulfate. Along with it, to liberates a hydrogen gas and 4 carbonyl atoms. The same time, it react with the most moisturized nitric acid to form a deep blue color complex, that is nickel nitrous acid, and releases hydrogen gas. That is nickel carbonate reacting with the nitrous acid in the water, that leads to the formation of deep blue color complex, that is the nickel nitroso hydroxide complex. Along with it leads to formation of hydrogen gas and releases 8 molecules of carbon monoxide. Okay, this is about the metal carbonyl compounds. How the metal carbonyls are generated? It forms the four kinds of metal carbonyls are generated with the four different types of bonding. That is the metal carbon, terminal carbonyls, bridged carbonyls, semi-bridged carbonyls, and triply bridged carbonyls. This triple in the terminal carbonyls, the metal ions is attached with the carbonyl with the single bond, and in the bridged carbonyls, first we can say a rigid carbon. The same metal ligand is bind with the carbon, generate the bond with the two metal ions. That is the bridged type of bonding. Then the coming to the semi-bridging, some of them carbonyl compounds are attached to this terminal, some of them are attached with the bridge. That kind of bonding is known as semi-bridge. Here we consider that the four osmium ions are binding with the six metal bonds, and it is attached with the one, two, three, four carbonyl groups are attached with the bridging bond. That is, this kind of structure is called bridging bonding of the carbonyl with the metals. Next, triple bridging. Same metal ion is attached with three metal ions. Same ligand is attached with three metal ions. Okay, metal carbonyl complexes. This is about the metal carbonyls. Tomorrow class we will discuss about the metal nitrosyls. Okay, thank you.